Okay, so start recording. Um, so if you remember last time, Alex, what did we go over last time? I was just talking about it.
So we covered like how just the basics of how neural networks are and the linear algebra behind it, the matrix multiplication, and then we covered like the different layers, so the input and output layers, and then in the middle like the hidden layers and how it forward propagates through. We didn't go over the back propagation yet.
Right. So um we're gonna go over backpropagation today, and we're gonna explain how do you actually train a neural network. So good. Now this is just the agenda for today. So quick recap of last time. I'll start off with a quiz like usual. And then how do we train neural networks? So we're gonna go over backpropagation, theory, implementation. We're gonna go over computation graphs, which is the under the hood sort of implementation of how this is actually performed. And if we have some time, which I don't think it's gonna be tough, but go over like some of the shortcomings of training ML models, like overfitting regularization, that type of thing. So quick recap so far. I have this quiz for everyone, that I will give you all 15 minutes to go through. But you should have, if you have access to slides, then it's in there. If not, I'm gonna paste it in the chats. And let me see. I'll start a timer for 15 minutes. Um, Whoops. So does everyone have access to that? Whoops. Does everyone have access to this?
Yeah, I have access.
Okay. Okay, perfect. So I'll give y'all like 15 minutes, and we'll go over it. And I mean, if everyone finishes before that, then we can just go over it sooner.
Hey Jose, I have to
What's
go,
up?
but I'm gonna
Okay.
watch the recordings. All right.
Sounds good,
Bye.
bro. All right, nice to see you. Take care. Mm. Ulysses, if you're just joining us, we're just like going over the quiz that I have in the slides. Do you have
Okay, I'm gonna
access
run and get
to
my
them?
headphones. I'll be right
Okay.
back.
What is okay. Sounds good. By the way, if you don't know something, you can don't feel bad. You can just leave blank, and that way we'll know.
Where's the link to the quiz?
Oh, it's I posted it in the chat, but it's also I'll send it again, and I'll go over it right now. But the slides are also in the Discord. Let me send it to you right now. I'll put it in the chat again.
Got it. Thanks.
My computer is being like really slow. I think I might need to get. It's not even that old. Okay, so I hope everyone had a chance to at least look at it. If not, we're gonna go over it right now. So how was it?
I found it pretty hard.
You found it pretty hard?
Yeah.
Yeah. Ulysses, what about you?
I found it as information that I should know fluently, and I do not.
Okay, well, in that case, then I'm glad that we're going to be going over it. So first question, what is linear algebra? Why do we care about it in machine learning? So linear algebra is a branch of mathematics that deals with, I mean, it's really like linear combinations of, yeah, like linear combinations, vectors, vector spaces. So like linear combinations and then how you would represent these linear combinations. The reason that we care about it in terms of machine learning is a couple of reasons. One of them that is neat is that it allows us to represent our data. So, for example, our training data, when we give it to the computer, sure, we might understand it by looking at it, like you might say, okay, house prices, etc. But you need to represent it in a way that a computer can understand it. So for that, we use linear algebra with matrices, with vectors. It also allows us to efficiently perform computations on that data because certain operations like matrix multiplication and the dot product lend themselves to parallelism, which is very efficient on hardware. So this is just like some of the reasons that we could have said for machine learning. Um, also the dot product is very important for us because the that going from linear logistic to neural networks, we see that we have this linear combination of inputs, which is our features and our weights. Whenever we compute that sum, that is a linear combination. Um, so linear algebra just allows us to do that, and it allows us to expand to multiple dimensions. So like you just to higher dimensions, infinity and beyond. Okay, so what is a vector? A vector, I mean, as you know from maybe like physics, it has a magnitude and a direction. Um, but I guess you could really look at it as there's a point in space and you want to know how to get to that point. Um, but an example of a vector, you could simply just give me 3 coordinates, 1, 2, 3. This would be like a vector in 3-dimensional space that has an x component like vx, vy, and vz, which is to say like to get to this point, go over 1 in the x direction, 2 in the y direction, and 3 in the z direction. Now, the reason we use it in machine learning is because it allows us to represent our data points. Because if we just look at our data points as points in this however many dimensional space, let's say 3D space, you could have 10, 100, 1000, and let's say that's like some house price or whatever. You can say like, okay, this is feature 1, feature 2, and feature 3. And then you can have a corresponding weight for each one. That would also be represented as a vector, right? W1, W2, and W3. And then, you take the dot product between the two, and that will give you your prediction, right? A matrix would be a similar example, but now you would have this list of vectors, I guess you could call it, but it's kind of just like you can imagine every row in and every column as well in a matrix is itself a vector. So it's kind of like a combination. It's like many vectors put together. But that might not be the right way to think about matrices. Well, we'll look at that later on. But they too represent linear transformations. But you can have multiple of. I'm just trying to put in the context of what we went over last time. But these would be like training examples. So if you have a collection of many different training examples, you can represent your data set as a matrix. Does this make sense so far?
Yeah.
Okay. Was there things that you all struggled on this, like on those questions? Okay. How do you represent a linear regression model using linear algebra? This is actually like fairly simple. So your regression model would be y, and then I would just write w0, also called the bias, but and then w1 plus x1 plus wn, so on and so forth, right? You have wn times, that's not supposed to be plus, it's supposed to be times, times wn xn. Now this looks like something that I've mentioned before. What is this? Okay, go down. So this is a dot product. I don't have the little dot thing, but it's essentially represented as a dot product because again, a dot product is taking the linear combination of these weights and these features. So when we compute the dot product, what we're doing is taking the sum of these like element-wise multiplication. So we have, the corresponding weight with its corresponding feature, and then we sum them all together. For the bias, typically, you'll see that in our weights vector, like it will often start as 1, and then you'll have like W1, W2. That's because if you have a 1 here and you're multiplying it, then your bias is just going to like 1 times whatever number is the same number. So if you multiply by your bias, then it's just going to give you your bias. And then when you add it all up together, it's going to look like this. So I hope that makes sense. And then for logistic regression, we have the same thing, but remember that here, y, which we can also call prediction, is going to be 1 divided by, and then this is 1 plus exponential function, which is e, to the negative z, where z is this right here, which is, like what we went over. It's kind of like it's a regression model inside this logistic model. The only thing is we're applying a sigmoid function on top of it so that we get our probabilities. Does this make sense so far?
Yeah.
Again, I'm just kind of like going over some of the. So assuming that you have a weights vector and a matrix vector that represents our data, what operation can we perform to calculate linear combinations of the elements? Anyone want to respond to that one? Let me see. Did y'all let me see.
Yeah.
Sorry, go ahead.
I didn't know if it was because I noticed like a difference between matrix multiplication and like a direct like dot product. So I didn't know which of the two it was.
Yeah, that's and I understand like it might be confusing at first, but this would be, I think like the most correct answer here would be a matrix multiplication. You can treat a vector like a matrix essentially. It would just be like either like one row or one column. And then you perform that multiplication. If I jump back to the earlier slides, recall, it was up here, somewhere up here. recall this one, like if this is my vector and this is my data set, then the operation I'm performing here is this is a matrix multiplication. So jumping back, and then how do we multiply two matrices where criteria must be met? I guess like to multiply two matrices, it does kind of like depend, but essentially like you want to look at the inner dimensions, and make sure that those match. So if you have a two by I'll just put in abstract terms, an n by m, an n by m matrix, and then multiply by an m by l matrix. So we can see that the inner dimensions here, so the first matrix has m number of columns, and this one here has m number of rows. So a column has a corresponding row. So this is important when it comes to the entries. If the sizes don't match, you know, like you can't perform the operation. And then the resulting matrix is gonna be n by l, which is the outer dimensions. In order to actually multiply, go through all the rows in the first matrix and multiply it by all the columns in the second matrix. So again, jumping back slightly, let's show this example. So go through every row in the first matrix and multiply by every column in the second matrix. The reason why the columns here need to match to the rows here is because if I have this row 2, 5, 2, and I have this column, sorry, the reason the columns need to match, so I have 2, 5, 2, that's the length of my row. And then if I have the rows here, -2, -2, 0. Okay, so the length here needs to match the length of the row needs to match the length of the column here, which is why we need to fit that criteria. Ulysses, you were gonna say something?
No.
Okay, so yeah, go through the rows of the first matrix and multiply by the columns in the second matrix, and do that for every row. Is there a difference between a dot product and a matrix multiplication? If so, explain the difference. I think Joe's might have put that question in there. Is there a difference? When you really think about it, you could argue that a matrix multiplication is really a series of dot products. Because if you look at the computations that are happening here, you see this down here that keeps changing. That's synonymous with a dot product. When you calculate this first entry, or I guess these like first couple entries, the way that you get this entry is this element is by actually performing a dot product between 252 and -2, -2, 0. So you perform a dot product here. A matrix multiplication, I guess, is expanding that and doing it over a wider collection than just two vectors. It's doing a matrix multiplication, which I guess you could argue could be like a collection of vectors. Does this make sense? So there is a slight difference. You could argue a matrix multiplication is just an expanded version of the dot product. So give me 2 reasons why linear algebra is useful in the context of machine learning. I elaborated on this a little bit up there. Who can remember? Who can tell me? Someone tell me one thing and someone else tell me another thing.
Efficiency.
Yes, exactly.
Yeah.
You
With
lose.
regards to the parallelism,
Yes,
that's
parallelism.
why it would be efficient.
What about some other stuff?
I'm not, but I just want to clarify efficiency because
Yes.
of the
Yeah.
parallelism
Yes,
that
that's correct.
okay.
That is correct.
And
Yes.
I I would also say that the way that it allows us to represent the data
Yes.
in a mathematical form.
Yes, perfect. Exactly. What is a feed-forward neural network? Let me see. What did you all respond to this? Yeah, Alex, you got it. A feed-forward neural network is comprised of an input and output and hidden layers. The calculations are done at each layer. Yeah, so why is it called feed-forward?
The previous layer as output provides the input for the next layer.
Okay, exactly. What's a perceptron? What are the components of a perceptron? Lord. So Alex, you're right. A perceptron is a single neuron. It is, I guess you could say, like the most atomic like part of a neural network. And then as far as the components, which by the way, I'm going to change these things to be like paragraph form instead of short answer because I can't go down here. So some of the components. First
Input,
we huh?
yeah, input, weight, and
Input.
output.
Exactly.
Oh,
Input.
you need a function.
Yes. Weights and bias. Um
Activation function.
Activation function. And then I guess implied, like before I write activation function, I'm gonna write linear combination of the previous of the previous elements. So linear combination of the inputs and the weights, right? And then an activation function. Exactly.
Is the linear
Exactly.
combination the input
Linear combination
of the
is
previous one of the previous
yeah,
function?
the linear combination is the essentially the dot product between the weights with the features. So it's the multiplication of these two things. Multiplication addition of these two. Plus your bias. You could call it we'll reference it today as a pre-activation. It's essentially this up here. Remember?
Yeah.
Okay. So how do you represent a perceptron using linear algebra? Oh no, let's call it P of X or Z. Let's call it P of A n minus 1. Why am I calling this P of A n minus 1? This is going to be P will just be my perceptron as a function. A minus 1 is the activation of the output of the previous layer. And then you could say this would be activation function. And then we're gonna have a n minus 1, and then take the dot product of that with our weights, and then add our bias. And this is essentially how
Oh,
that would be.
okay.
I like that oh moment. I like that realization. I like that oh moment. What is a okay. what is a layer in a neural network? There's 3 types. So remember, there's the input, hidden layers, and output layers, right? Input layer is just like the initial features. Hidden layers perform intermediate calculations. Output layers are final output. If a layer in a neural network has 5 neurons, what's the output going to be? Alex, you probably don't know for this one. So it's not a trick question. We're just gonna have 5 activation outputs. That's it. That's all I was getting at. So if you have like 20 features that come in um into a layer, let's say this is hidden layer 1, um and there's 5 neurons there, then this hidden layer 1, if it has 5 neurons, then it's gonna output 5 activation outputs and then pass it along to the next layer. Not a trick. I wasn't trying to trick anyone. What is a forward pass? How do you calculate this? What is a forward pass? So a forward pass would be you doing performing the calculation, how do I say this? The prediction calculations from input layer to output layer and everything in between. So like in between you have the hidden layers, and the forward pass is just going to be these series of calculations all the way from input to output, right? One way that you can like show this is to say that the output is gonna be, let's say I have 2 layers, so I'm gonna have it starts off a little nested. So you start off, let's say, like with hidden layer 1, um, and that's going to be like your input, which is X times the weights of your first like all the weights of the first hidden layer, like of all the neurons on the first hidden layer. So this has an output, right? But then this is nested within, let's say I have another hidden layer. So this is gonna have some sort of output. Then I'm going to do the same thing where I have these now become my activations, right? And then I have the weights of the second layer, plus the bias, and then let's just say I have whatever output layer. And then it's just going to, like it's the same nested thing. So weight output plus B, right? So we have like this sort of nested thing. This is just representing the activations of the previous layer becoming the inputs of the next layer. Does this make sense?
Yeah.
Yeah.
Thumbs up. Okay. So what is an activation function and why do we need it? What would happen if we didn't have an activation function? Yeah, Alex, I think you got it. It changes the output from a simple linear regression. Why don't we want to output a simple linear regression? What's wrong with that? Alex?
Like why wouldn't we want to?
Yeah.
I don't really know. Like, it just wouldn't like fit. It depends on like what your goals are, I guess, with the network.
Yeah, so recall that when we have just so
Yeah.
what do we need activation functions.
It adds
Um,
non-linearity to the.
yeah, it allows you to fit nonlinear relationships as well. If you did not have activation functions, you would just get a straight line, which straight lines are fine, but every single data point, like every single trend in data is not linear. So um, we want to showcase nonlinear ones as well. That's good. Some activation functions that Alex, you listed sigmoid and relu, which is good. I'll go over relu probably next session. What's the benefits of having multiple neurons in a single layer, and what's the benefit of adding multiple layers? So Alex, to your question that you alluded, yes, like it makes adding more layers makes the computation more efficient in the sense that like the network can learn more efficiently. But part of the reason, so having multiple neurons in one layer can divide the responsibility. So like some neurons will learn certain patterns, whereas other neurons will learn other patterns. Perhaps in your brain, when you look at something that's red, there's some neurons that identify that and make sense of that. And then as the network gets deeper, then you can extract more complex patterns. So I don't know if you see like a red and then you see that it has like an octagon shape, you're like, whoa, maybe that's a stop sign. So maybe the early layers pick out edges and colors and like simple features, and then the later ones, they kind of like take this and produce more complex uh features to be like, okay, so this is what we have. Okay, so and then yeah, manifold theory. Um anyways, that sorry, I hope the quiz was useful. I feel like it takes a very long time though. Okay, so I want y'all to try this out for yourselves. I'm For the interest of time, I'm gonna give y'all like 5 minutes to try it out, and then I'm gonna go over it. What I would recommend is make a copy of this. Um, this is um, this is essentially like a blank. Um, it's just like a blank like neural network. So sort of like just um, wait, did I have? Did I put the blank one in there? Let me see. I hope this is blank. Yeah, this is blank. Okay. I went to the wrong one. Um, so it's just like a blank implementation of a neural network. Just try it out. I'll give you like 5 minutes. Does everyone have access to it? Well, what I would do is go file and then do save a copy in Drive, make a copy, do your try it out for yourself, and we're gonna check back in like 5 minutes. Okay.
And where do we find the link to the GitHub? I mean to the
I
collab.
I put the link in the chat and it's also in the slides.
Okay.
Okay. I know that wasn't much time, but is everyone cool if I go over it? Thumbs up, maybe, if that's cool.
Yeah, go ahead.
Okay. So yeah, this is just like a blank implementation of a neural network. You know, so we have our simple neural network class. Let me import NumPy first, actually. And by the way, if we implement it correctly, well, let's just go over it. So we have our input size, which is just this is the size of our input layer. Then we're gonna have hidden size, which is the size of our hidden layer. And output size, as you might tell, is the size size of our output layer. It corresponds to the number of neurons. Same thing for this one. Corresponds to the number of neurons. So let's write out a simple example. So just you might be familiar with Java and not with Python, but self is basically the same thing as this. Self in Python. Anyways, I'm not gonna give you a Python tutorial right now. This is just for knowledge. So when we initialize our class, we're gonna pass in these parameters, and you know, initialize our function this way. So next, we want to, yes, initialize our weights and our biases for our model, right? So I am indeed going to do what they have there. So if we have well, we can, so let's make two hidden layers. Or yes. Yes, let's make two hidden layers, I believe. So we're gonna have oh dude, it's gonna want to, yeah, so I have self.weights, and I probably will put it I'll write the weights of the first hidden layer as self w1, and then yes, it's gonna be np.random.rand n. And so if I have here input size and hidden size, what this is saying is it's gonna be in the form of I guess you can kind of see this as like features are coming in, And then we have our hidden layer. And then our hidden size is going out. So that's kind of like one way to look at this. But essentially, the weights here, what you're saying is that they will have the form of, let's say I have, let's say, um, input size is 2 to make it simple. So this NP random, it ran like it's just making like a matrix for me essentially. np.random.rand. Like when you do this, it kind of just gives you back a matrix. And if I have here input size as 2, and let's say my hidden size is also 2, then this is going to be in this format, where I have, I don't know, let's just say this is like 0, 1, and this is 1, 0. Then what I'm essentially saying is I have these 2 neurons, and each one is gonna have a corresponding weight for the input, right? And the hidden size is telling me how many of these neurons I should have. So if I was to go up to 3, then I would have 3 neurons here. So let's say this is 1, 1. Does this make sense? I hope this makes sense. Right? I hope I'm doing this right. Yeah, you see 2, 4. Well, hidden size is 3. Sorry. If my input size goes to, okay, so like what they're showing you here, NP random 2, 4. So you're gonna have these 2 rows and these 4 columns. So actually, if hidden size goes up to 3, then what you would have is an extra number here. Not on the other one. What it's, hold up. Let me validate this. I mean, this would be true. This is right. I'm trying to think of when you perform the calculation. I think these 2 need to be equal to each other. At least your input size and the weight within your neurons need to be equal to each other. So okay, let's do the bias real quick for the first one. Perhaps that might help us understand this a little bit better. So the bias. So we're gonna have by the way, this 1 that they put on there, I always try to built-in function NP zeros. So you see it has hidden size. Okay, so this is going to be in the shape of, so we have 1 row, and many columns. So that's gonna look something like this, where you're gonna have 0, 0. So if our input size is 2, oh sorry, it's saying if our hidden size, sorry, hidden size is 2, I should say 3, we're gonna need 1 of these for every single one of the neurons in that hidden layer, right? Because you need to do this linear combination for each neuron in that hidden layer. Does it make sense so far? No.
Yeah.
It's here. It's input size. And we can just do the same thing for a different, like another one. So actually, no. When it's receiving, if you're linking these together, the output of the other one needs to be the same as the input of the next one. So this would just be self dot hidden size, and then this will be self dot output size. So this would be activations coming in. Then this is hidden layer 2. And then you have your output size. I hope that makes sense. Does that make sense so far? And this is
Yeah.
gonna stay the same. Oh, sorry. Go on. Yeah, this is gonna stay the same. Okay, so moving on to sigmoid. If y'all have any questions, please let me know. Sigmoid is just, as you know, it's gonna be 1 divided by e to the negative z. Sorry, 1 plus this is in there. So okay, we've seen this quite a couple times by now. And finally, for our forward pass, so to calculate our first forward pass, we do so Z1, which is going to be the pre-activation, I guess you could say. I'll just do this, but yeah, so this is the pre-activation or linear combination of the first hidden layer. Hidden layer. So pre-activation linear combination of the first hidden layer, and then this is, activation of the first hidden layer. And then you have this is you're gonna have the same thing for the next one. So recall that the way that we're doing this is our input here, right? Our features. And then we're taking the dot product between these features and the weights that we have plus our bias, right? So essentially the length of the features needs to be equal to the length of this weights one right here. If you were to take the length of that, it'd be the number of rows. So actually, your rows here correspond to the. Oh yeah, sorry, my bad. I got that confused. So your rows here correspond to. This might seem a little weird, but the rows are actually what correspond to the weights. So, for example, the way that there is represented, is this is weight 1 for the first neuron. The next one is weight 1 for the second neuron, and this is weight 1 for the third neuron. I know this might seem a little weird, but it makes sense mathematically. And then this would be weight 2 of the first neuron, and then this is weight 2 of the second neuron, and weight 2 of the third neuron. Does this make sense? Maybe? No? I hear silence. I hear crickets.
Yeah, I'm starting to get it a bit, but I mean, at first it was a little confusing, but it's making more sense
I know.
as we go along.
I know it can be a little confusing. I know it can be a little confusing. But when the reason we know it has to be like this is because you see that the rows here indicate the input size. So if I have two the rows here indicate the input size. If I have 2 inputs, then I need 2 rows, right? But then hidden size
Mhm.
is the number of neurons. So what this is telling me is, okay, so the rows need to match with the input and the columns need to match with the number of neurons. So what that's telling me is I need to have a column that corresponds to every neuron, and I need to have a row that corresponds to every incoming feature or incoming like activation, right?
Okay.
Um, so yes, it would be like this. I know. I'm sorry. I apologize if that's confusing. Uh, I didn't make the rules around here. I, anyways, and then if we implemented this right, I'm just gonna copy paste some of the previous things that I had just to show the example. Um, just making like a random data set. So hopefully that compiles. And if you run this example, by the way, this here will initialize it to an input size of 3, a hidden size of 4, and an output size of 2. And then if we run our example, so example forward pass, um, what did I put here? Of course, why would it go right? Did I mess something up here? Z2 might be in the way that this is defined. Because I think this one, what? I have hidden size, input size. Excuse me? Cache dot and then dot forward. Print the shape of the first couple. Operands could not be broadcast together with shapes. Okay, 100 to 14. Did I make the random? Three features, but what did we specify here? Yeah, input size of 3, hidden size of 4, output size of 2. Why do things not? Okay, let me copy the one that I had beforehand, even though it looks the same. But maybe I'm wrong. And then we can see what the difference is if it works. Has no attribute B1. But Just put these lowercase. Really looking same thing. Where? Okay, I think it just. I thought they were both lowercase. Only one is lowercase. Still work, man. You kidding me? Yo, help me out here. Dude, it worked before. What is the difference now? Might be definitely doing something wrong here. Yeah, shapes mismatch, right? Produces an array 102 since NP dot A1. Yes, A1 this here produces an array. Did I maybe give me 1 second? Hidden size. Output size. Input size, hidden size. NP dot A1 produces an array 102 since A1 has shape 104 sub has shape 42, so has shape 14. Broadcasting rules, yeah, fine. Incompatible for broadcasting. Indeed, indeed. Oh. Size. Change the shape of B2 to match the output size. Oh, sorry. It's right here. It's supposed to be output size. Whoops. Is that the difference? That is the difference. Apologies. W2 here is our, so our last hidden layer is our output layer. My bad. There we go. Do you understand like why I was getting the issue? I had hidden size here when it was supposed to be output size because this is the output layer. So this is activations coming in, and then this is the output layer. I hope that makes sense. Apologies. So now it works. Okay, so I hope that makes sense.
Where was it? Point out the change again.
Right here. So when I made when I was making the neural network,
Mm.
I put hidden size here when it's supposed to be output size because this bias corresponds to the number of neurons in our output layer, which is the output size. It's this one here. I really do have to move on though, because I haven't even gotten to like the main content of the lecture yet. Question, does the refreshers, like, I know they're helpful, but like they take up a lot of time. Is it cool with people or maybe? Okay.
Yeah, I
Anyways,
like. I get something out of it.
so let's refresh our memory now that we've done this. So now that we gone over the forward pass, how do we go over training? So before we look at training neural networks, let's see how we train logistic regression models. So recall that our logistic regression model look like this, right? You've seen this like a dozen times by now. But you have your sigmoid function, and then you apply the linear combinations on top of it, right? We're fairly familiar with this so far. Recall also our binary cross entropy loss function, which looks a little scary, but it's mostly just this right here. This is just taking the sum over all the training examples, but this comes from physics and information theory. But essentially, what you have is when our true label, when our true output is supposed to be 0, you can see that this yi here, this term cancels out. Like it just becomes 0. So we're only left with this term. This term is telling us how far off the prediction was from the true label. So notice if the true label is 0, this here becomes 1 minus 0, that's just 1. It just leaves us with this term. So really all we really want to look at is this term, which is 1 minus, and then it's going to be the probability here, right? If the true probability was 0, right? Log of 1 is what? What's log of 1? I know it might be a long
0.
time. It's 0, right? And that's what we see over here. Because if we have 1 minus 0, log of 1 is 0. That's what this value correlates to here. If we have the inverse scenario where our true y value is 1, then now we see this whole term cancels out. This here is 1 times log of p, and then we're left with the same thing. And log of 1 is, again, as we discussed, 0. That correlates to this side of the things here. Everything in between would be some sort of loss. If the model very confidently says that let's say that the true label was 1, right? So this whole thing cancels out. We're only looking at this. If it very confidently says that it's 0, let's say that it's like, let's say it says it's 0, right? What happens here? Oh, sorry, here. This asymptotes to infinity. So what you're gonna get is this is gonna be a very large number, very large number. It's going to be a very large negative number because if you understand log as the and by the way, I'm gonna send like a video that's really good on max log likelihood that goes over this, but if you understand log as the opposite of exponential, like some e to the negative infinity is 0. So we put this negative in front of it to make it positive. But moving on, so remember how we optimize our parameters, right? What's our goal? So we had that loss function that tells us how we measure the correctness of our model. And we want to find the optimal parameters, W star, B star, the ones that we were randomly initializing before. And remember that to update our parameters, it's simply just the old value that we have minus the learning rate times the gradient for that parameter. Same thing for the bias. And the primary computation here is calculating these gradients. So again, we're calculating gradients. Very briefly, recall the chain rule. Recall that if you have nested functions, so f of g of x, the derivative here for this function is going to be f prime of g of x times the derivative of the inside function, which is g prime of x, right? So we all remember this, I hope. So how do we calculate the gradients for logistic regression? Well, how do we calculate? By the way, j is the cost function. The difference between the loss function and the cost function, they're really the same thing, but the cost function is the loss function aggregated over all the training examples. That's why it's usually like an average. It's an average of the loss for all the training examples. So let's calculate the cost for a specific weight. Essentially, what we're asking the question is, how does this weight or this bias change our loss, our cost function, right? We want to minimize our cost, so we want to make the changes that will minimize this. Again, we've seen this before. So we start off with our loss function, which we have right here. By the way, P here correlates to the output of the sigmoid function. So I actually wrote this, I did this by hand. So I hope y'all can appreciate this at least. It was pretty fun though. So you have our loss function, which is, it has two parameters that I put here. One is our true label, and the other one is our prediction, right? So then we studied that the loss function looks like this. Also, like I said, the prediction here is given by the output of our sigmoid function, which just looks like this. And for simplicity, I kind of express it as 1 plus eta negative z eta negative 1. And remember that z is the linear combination of inputs. So if we find a partial derivative of the loss, if we want to find a partial derivative of the loss with respect to a specific like w parameter, you need to take the chain rule. So if you want to take the derivative of this loss function here, with respect to wj, well, wj is like in the z somewhere, right? It's going to correlate to, like, let's say it's y1, right? It's somewhere in here. Okay, for me to get the derivative of that one, what do I need to do? I need to sort of unravel this function. So this p, so I need to take the first the derivative of the loss with respect to the sigmoid function, which we symbolize here. And then that sigmoid function is also going to have a derivative, right? And I want to get the derivative of that with respect to z, which is what contains my weights. And then, of course, this linear combination also has, it's also a function, so it has its own derivative. And that's this is the derivative of this linear combination with respect to this weight. Does this make sense so far? I understand the notation might scare people, but I hope this makes like intuitive sense so far. It's just a chain rule that I went over last time. Yes? Hello?
Yep.
Okay.
Yep.
So taking and just like skipping forward and like just doing the derivatives right here. So if you take the derivative of this function with respect to p, then this is what you get. You can verify that yourself. Same thing with the sigmoid function over here. This is the derivative that you get. And, you know, like if you take the derivative of this z with respect to wj, all of them become constants, and you're only left with the coefficient of that term. So you get xj. This is just me simplifying a little bit. It's really just simplifying. As you can see here, I'm just finding a common denominator, and then I'm rewriting this. You can actually rewrite this to be 1 minus p times p. I'll let you take a look at that afterwards. And then finally, what you're left with after you simplify is this very neat equation, which p minus y times xj. P is our prediction, y is our true label, xj is our feature. So what we're saying is the derivative of the loss function with respect to that parameter, wj, is just going to be our error times the feature. Neat, very neat. J is the cost function, which is simply just the average of all the average loss of all the training examples. So that looks like this. So if you take the partial derivative of that one with regards to loss, it really just becomes the summation of this. I hope that makes sense. As an exercise, you can do the same thing for the bias, but long story short, you get the exact same thing as the other one. It's the error, but the bias is a constant. The derivative of a constant is 1. I mean, sorry, the bias is just like its own variable. The derivative of variable is just 1. So you end up with this. And you do this for like each training example. In case you didn't like my handwriting, I also wrote it out for you in the slides. And then, you have your final grading computation. So did that make sense to everyone so far? I understand. The math might get confusing. I apologize. Alex,
It makes
you were
sense.
Okay, beautiful. So back propagation a little bit. So remember, a single neuron is analogous to logistic regression, which is why I was going over it beforehand. So how would you find the optimal parameter for a single neuron? Can someone tell me? If it's analogous to logistic regression, how do you think we would do it? Maybe? No? Okay, I'll just tell you. It depends. If you said that you could do it the same way as logistic regression, you would be right if it was in the output layer. But how would you calculate it for a neuron that is not in the output layer? What if it's in a hidden layer? So remember the forward pass, forward propagation, where we are just chaining these, like stringing these activations together, right? And it's kind of like a nested function. You're gonna see that this nesting chain here lends itself to the chain rule as well. So what if the neuron is not in the output layer, if it's in the hidden layer? Well, what you're gonna have to do is the parameters W and B of our neuron influence its activation A. The activation then influences the pre-activation Z out of the next neuron because the activation is now the input to the next neuron. So essentially, this neuron here, output layer neuron, is going to be affected by this neuron in the second hidden layer, right? And that Z out influences the final output, A out, which is what's used in the loss function J. So the core problem is, how does a small change in W in our hidden neuron affect the final loss, J? The effect is you have to propagate this backwards. We'll see that right now. So if you have this output function, what I've written here, if you take the derivative of this, you're going to see that it's a function within a function. So we're just going to be taking those chain rule derivatives going backwards. So the chain rule revisited. So if you want to find the cost for a particular weight, you need to find, okay, so what was the cost for the output that I just gave? And then you need to find, you kind of like chain this together to say like, okay, what was then the derivative of the output with respect to the change in my pre-activation? Okay, but my pre-activation for the output layer depended on my previous neuron. So how did my pre-activation of the output layer change with the activation of the previous neuron? Yeah, but the activation of my previous neuron depended on its pre-activation. So how does that change? And the pre-activation of that neuron depended on the weight. I know I just said a whole string of words, but does that make sense? I'll show you visually up here what that looks like. What we're saying is, okay, you need to find the how the loss function here changed with respect to the output of this neuron. But the output of this neuron, the activation output, depended on its pre-activation, the Z out, right? but that Z out was dependent on the activation that it received from this hidden layer here, from this neuron in this hidden layer. But the activation of that neuron in that hidden layer depended on its pre-activation, which is essentially like this here. And that pre-activation, as you can see, depends on W. So if we want to find the parameter W, then we need to do this chain right here. Please tell me that makes sense.
Yeah, it makes sense.
Okay, beautiful. So now that so then why do we need backpropagation? Well, the process of calculating those gradients layer by layer going backwards to signal how we change that specific, how we tune that parameter, we need to use backpropagation for this, and I'll show you what that looks like. But this is a very efficient algorithm in order to compute this. But first, let me show you how the computer does it using computation graphs. So you understand that neural networks, even simple ones, is really like a sequence of operations, right? You have your input layer, you calculate this first, and then you send that to then this sequence of calculations, and you send that to this sequence of calculations. So you can represent that with something called a computation graph, where the nodes here represent your input variables, and the edges will be operations. So if you have X, Y, and Z, let's say you have X is 1, Y is 2, Z is 3, and you have X plus Y times Z. So you calculate, let's say this first, so you get 3, and then you do 3 times 3 is 9. Let me show you with an example I drew out. So let's say I have E equals A plus B times C plus 1. So I have 3 like input variables here, like 3 nodes. Let's say A is 2, B is 3, C is 4. I'll show you the forward pass later, but it would kind of look like this, where I would have A and B, and we add these together to get this node D. And then C plus 1 is going to give me this node F. And then I'm just going to multiply D times F to get E. This is pretty simple to understand, right?
Mm-hmm.
Yeah. So a forward pass looks like this, where you just replace, like this with the values, you perform the computations, and then you get your final output as a result. Now, here's where it gets fun. When you have an example backward pass. So up here, I did the forward pass. And let's say I do this backward pass, you get your error, which I did not take, I didn't actually use this for anything in this example. But first, you kind of want to know what is the change in the final output E with respect to E? Well, it's just gonna be 1, because a derivative ddx over ddx is just 1. Essentially saying the rate of change with respect to yourself is constant. And then you flow backwards to say okay, so how does what is the partial derivative of E with respect to D over here, this one? Well, if you perform that computation, you're gonna see that it just ends up being F, and which is just 5. And then similarly here, oh shoot, I think I copied that twice, but that's not okay. This is supposed to be the partial derivative of E with respect to F,
F.
which is just going to be D, and D is also 5. Probably why I got that confused. So again, the D and the F, those are coming from here, by the way. You can see that if I go back to the forward pass, like this one, so this D and this F, they're coming from here, and these gradients, like these derivatives, are flowing backwards to the earlier nodes. And then you perform this all the way back until you get to your like these inputs, right? So just taking like this route as an example, the partial derivative of D with respect to A is 1 because, so again, this is why we need this back propagation. In order for you to calculate the derivative of E all the way at the end with regards to A, this initial one here, it's a partial derivative of E with regards to D, so this one, and the partial derivative of D with regards to A, which is this one. And the chain rule tells us that we need to multiply these together. So ultimately, the partial derivative with regards to of E with respect to A is 5 times 1, so it's just 5. So again, this is telling us how this parameter A changed the final activation all the way at the end. Does this make sense? Okay, perfect. I don't know if silence is good or bad, but I also like put a little explanation here. But essentially, with a neural network, you would have the same thing where you have your cost and then you're flowing these gradients backwards to say like, okay, so what was, let's say this is my output layer, which is, I'm just calling activation 2 here. And then you're saying, okay, what's the cost with respect to this activation 2? Okay, it is whatever this gradient is. And then for you to update the previous parameters, you say, well, what is the cost? Like how did our output change because of this weight? Okay, for that I need to calculate this derivative here, which is going to be dw. So it's going to be this one here, the cost with respect to the activation of A2, the partial derivative of the activation of A2 with regards to the pre-activation Z, and then this here, the derivative of W2 with respect to Z2. I hope that makes sense. But essentially, like you're taking these derivatives all the way back, and it's just a way for you to do the chain rule very efficiently. So I provided a little explanation here, and then I also have a backpropagation implementation that I want to go with y'all, but I'm not sure if I might just leave this here, because I know we've been running for a while. But what I highly recommend is that you go in here and you try to implement this yourselves. This is a blank example. I have a real example that I have the solution here. I'll give you the solution as well for you to reference. But first, what I would recommend is to try to implement this yourself, where I have here write code here, write the code, and then reference back the solution. Okay? Yes?
Sounds good.
Yeah, apologies. And then we'll go over it at the beginning of next class. But next time we're gonna go over training with Jax and with and doing some Kaggle examples, or doing some like real examples, so that you can get a better grasp of some of these things. Any questions? Okay, I'm going to post the 2 notebooks in the Discord. So that you all can try out the example, the blank example with the solution as well. Okay. I'm stop. I'm gonna stop the recording.